Well, hello, everyone. It's 1 p.m. Eastern, and that means it's time to begin our 86th CoCoRaHS Weather Talk webinar. A very warm welcome to you all today. I'm your host, Henry Regis. This week, I'm also running the technical side of our program, as Noah Newman is off on assignment. So if we have any glitches, you'll know why in advance. We're coming to you live from the Colorado Climate Center in Fort Collins, Colorado, on what has been a wet overnight. But the sun is starting to break through here shortly. All of our Weather Talk webinars are sponsored by the generous donations of listeners just like you. Well, today's webinar, we will take a look at turbulence, the influence of thunderstorms on aviation turbulence to be exact. And this is presented by Stan Trier of NCAR, located in Boulder, Colorado. And if any of you have flown before, you've probably experienced turbulence. And so this will be an interesting talk to see how it occurs, where it occurs, and I'm sure you'll enjoy it. Stan is a project scientist in the Mesoscale and Microscale Meteorology Lab at NCAR. His research interests include mesoscale convective systems, large groups of thunderstorms, that is, environmental factors influencing thunderstorm initiation, and effects of thunderstorms on aviation turbulence. Stan is originally from Western Massachusetts, that's just west of Boston, and he received his BS degree in meteorology from Florida State, his MS from Penn State, and meteorology as well, and then his PhD he did here at Colorado State University in 1997. Stan likes to cycle, he likes to hike, he loves outdoor stuff, and so let's give a big CoCoRaHS welcome to Stan. It's great to have you with us today. We've all experienced the bumpy stuff, so we're looking forward to seeing what you have to tell us about that. I'm not a big fan of those. I put my seatbelt on tight when I start bumping around on the plane. So, hey, Stan, so as we start off today's program, I'm going to ask you a question that I pose to all of our guests, and that's, how did you become interested in meteorology?
Well, I grew up primarily in the Boston area, Henry, and I was very fascinated by East Coast snowstorms and the prospects of missing a day of school because of them, which didn't happen often enough. But so I've had a lifelong interest in meteorology. Before that, I, as a small child, was in Wisconsin and was terrified of tornadoes, and my fear of severe weather actually turned into fascination. So I've been very fortunate to have worked a long time in the field of research meteorology. And I'm very happy to talk to all of you today about aviation turbulence. And I really appreciate CoCoRaHS. I'm a big fan. I look at it every day. And as Henry mentioned, we've had a much needed spring rainstorm in the Front Range overnight. So I looked at it just this morning to see how much rain we got in my neighborhood, 0.8 of an inch in the last 24 hours.
Oh, you did pretty well. We only got around 0.4 here, so that's great. Well, Stan, take it away. It's all yours, and we'll come back at the end of your talk to take questions from our listeners. Thank you.
Thank you, Henry, for the very nice introduction. As Henry mentioned, I'm going to talk about influences of thunderstorms on aviation turbulence. And I'm actually trying to get this to advance here. I'm having a little trouble. Let's see if I can. No, I'm unable to get it to advance beyond this title slide. Can others see Henry, can you see?
No, it looks like we're back on the title slide. Why don't you pop back out of that again and see, so we'll do this, stop sharing your screen.
Okay.
There.
All right.
And then do maybe the shear, or even if you don't have it in the full,
Okay, now
I think we could try
let's
it.
see. Can we go to okay, here we go. it showed up on my screen. Can everyone see the outline?
Well, now you got to do share your screen again. So go ahead.
Oh, okay.
Share your screen.
Okay, let's see.
This is where we miss you, Noah Newman, trying to figure these things out.
All right, share screen. Yeah. Okay, now I'm gonna.
Yeah, that'll work. But if you want to try it,
I have some animated images in here, so let me see if I could just try to go to slideshow one more time and see if
just from the beginning
from
there.
Current slide.
Yep.
Can you see it? And let me try to advance it one.
There we go. You were good.
Okay, all right.
All righty.
Okay, well,
take it away.
I'm the primary objective of my talk is to use research numerical weather prediction model simulations to investigate mechanisms for aviation turbulence. And I'm going to focus particularly on thunderstorms with an emphasis on turbulence that occurs outside of the thunderstorms, but is very much influenced or generated by the thunderstorms, because that's much harder to diagnose and predict. So I'll start off with a little bit of background on the importance of turbulence to the airlines, and also on how turbulence is reported and measured. The primary aspect of the talk will be to looking at these mechanisms for thunderstorm-generated turbulence. And a lot of times, turbulence, or rather thunderstorms, generate waves in the surrounding air. And these waves are often the linkage between the thunderstorms and the turbulence that is occurring outside of clouds. And sometimes we can have wave breaking occurring above the thunderstorms, which is associated with strong turbulence, but also waves moving horizontally away from the thunderstorm regions can present or can help develop turbulence. Also, another thing that happens with thunderstorms is up near the jet stream level, they have strong horizontal outflows. The air goes up in a thunderstorm and then spreads outward near the tropopause or jet stream. And in these regions where there's a strong enhancement of the jet stream from the thunderstorm outflow at levels just above or just below where this jet is the strongest, you can have areas of strong vertical wind shear, and that's either the strength of the wind speed or the directions of the winds changing quite a bit with height. And that's also presents a situation that is very conducive to turbulence. In the final part of the talk, I'll talk a little bit more about prediction of thunderstorm-related turbulence and what we can do with these research simulations, which are sort of done after the fact, but they have the advantage of having much higher resolution, so they can capture physical processes that lead to the onset of the turbulence, that are directly responsible for the turbulence. Unfortunately, they're not high enough resolution to be able to simulate the fully developed turbulence, but they can really help you diagnose the mechanisms for the causes of the turbulence. Now, for real-time forecasting, operational weather forecasting, for various reasons, which I'll get into shortly, we have to use models that don't have such high resolution, and they cannot directly simulate the turbulence. So our approach to forecasting needs to be more statistically based, and I'll talk a little bit in the final part of the talk about how that's done. Just in terms of background, turbulence has large economic effects on the airlines, about $200 million per year. It accounts for about 75% of air carrier accidents. And about 10% of these accidents, and by accidents, these are the types of, this is not garden variety turbulence, but these are the events that you hear on the news. They can actually result in some significant damage to the aircraft. And I have an example on the right showing a wing that was destroyed from an accident about 30 years ago near the Colorado Front Range. Most turbulence events certainly don't cause this kind of structural damage to the aircraft, but over the aircraft's lifetime, they can, it adds up and it causes increased fatigue to the airframe and a shorter lifetime for that. It's also bad PR for the airlines. It contributes to the public perception that air travel is unsafe, and it actually is very safe. It's much safer than jumping into your car and just going for a car ride. So I hope some of the some of these movies and animations that I'll show you about turbulence events won't dissuade you from flying in the future. It's really very safe, but it is an important problem to the airlines, and it is the second leading weather factor affecting air traffic control or workload, just behind issues of visibility that can crop up. So it is something that the airlines take very seriously. Now, how is turbulence reported? Well, the primary way are through these PIREPs, which is an acronym for pilot reports. However, there are some issues with PIREPs. They are aircraft dependent, so they don't tell you exactly how strong the atmospheric turbulence is. They just tell you what the pilot perceives or the first officer perceives as the strength of the turbulence. And it's broken down into 3 different levels: light, moderate, and severe. And there's a little bit of a guideline on the right. In a nutshell, light turbulence, just as an example, if you have a coffee cup on your tray on the aircraft, you'll see swirling of the liquid in the coffee cup. You might feel being pushed against your seatbelt a little bit. It's a little bit jarring, but it's usually tolerable for most passengers. Moderate turbulence is much stronger than light turbulence. At that point, you'll often get spills with drinks on your trays. Dining service or beverage service on the airlines is almost impossible when there's moderate turbulence. It's usually just before moderate turbulence that the captain or the first officer, or when they anticipate moderate turbulence, they'll tell the flight attendants to take their jump seats, for instance. When we get into severe turbulence, service by the flight attendants is impossible. Stuff goes flying in the aircraft. People will get injured if they're not securely belted into their seats. So as I started to allude to, there are some issues with pilot reports. For one thing, when the crew are in turbulence, they're usually trying to avoid it and don't have time to actually make the reports right then. So the location and timing is not always completely accurate. They tend to be indexed. These reports are indexed to the nearest airport, so there's some uncertainties in the exact location. So we really need an atmospheric, to understand the turbulence, we really need an atmospheric measure of turbulence that's aircraft independent and can be reported automatically. And it turns out in the last 20 years, that's been developed. And we have these systems on a subset of the commercial aviation fleet. And these systems report a quantity or metric referred to as EDR, and that stands for the energy dissipation rate. Unlike the pilot reports, it's quantitative, it's exact. The location and timing are accurate. The software resides within the avionics system of the aircraft. And these recorders are able to diagnose the EDR and report averages and peaks over 1 minute time intervals. They're automatically generated, as I mentioned, and downlinked, and they're available on a few different meteorological data streams, including AMDAR. And I have an example at the right, which shows they're on a subset of these of commercial aviation flights. I would say if I had to pick a number out of my hat, and this isn't an exact number, it's about maybe 5 or 10% of the flights over the continental US. This is an example of flights around a complex of thunderstorms in the high plains, and the green colors show smooth air. These are 1-minute reports. The yellow colors are for light turbulence. The orange colors, which you see on the south end of this particular complex of thunderstorms just outside, are moderate, and there are a couple of reports of severe, which are in red. So these are very helpful.
Let me jump in here real quick. Are there certain planes, so larger planes have these, or is it just scattered throughout the fleets?
These are on 737s, 767s. It's a variety of planes. It's really more specific to the airlines. At the current time, Delta has a lot of reports. They used to be on Southwest and United more. We sort of rotate them on and off. And we're trying to get them on more of these different flights. But that's a very good question.
Okay,
and
thank you.
They're really useful after the fact if you want to go back and look at some of the mechanisms responsible for turbulence in a particular case. Very, very valuable information. And also they also help air traffic controllers. They have access to these reports in real time. So they can help for flight planning and turbulence avoidance. So very, very useful thing that's developed in the last 20 years. So I wanted to first talk about some of the different sources of turbulence. There are many different sources. Up near the jet stream, there's clear air turbulence that's associated with strong wind shears both above and directly beneath the jet stream. And you can also, in this diagram, you can see wave breaking. And, as I mentioned, waves are important for turbulence, and waves by themselves are not hazardous, but under certain conditions like strong wind shear, the waves will break, just like waves at a shoreline. If you ever go body surfing, when the wave is overturning on itself, it's developing foam, that's where it's very rough. It's a similar situation in the atmosphere. Another source of turbulence is flow over the mountains, can generate mountain waves, and they can break. This is often an issue in the lee of the Rocky Mountains, for instance, near Denver. And there's very routine type of turbulence. If you've ever taken off on a summer afternoon when there's a lot of heating near the surface, near the boundary layer, there are thermals. This is convective boundary layer turbulence, which I have indicated right here. And to the right is more the subject of this talk. It's turbulence associated with thunderstorms, which are deep clouds in the atmosphere. Obviously, it's very hazardous to fly into the thunderstorms, but the airlines are usually pretty good at avoiding that. There are only situations where they can't avoid it every once in a while, where they look for a weaker area of the thunderstorms and have to penetrate the thunderstorms. But there's also turbulence above and laterally displaced from the thunderstorms. So that's the subject of this talk today, turbulence above and laterally displaced from the thunderstorms. It's estimated that about 20% of turbulence at aviation cruising altitudes up near the jet stream, that's 20 to about 40,000 feet above the ground, is thunderstorm related. And I do believe that these estimates would be much higher if the out of cloud turbulence generated by the thunderstorms could be more widely and easily diagnosed. The out of cloud generated turbulence, just like standard clear air turbulence, is invisible. So it's hard to diagnose using the standard hazard identification technologies such as radar, satellite, and lightning detection networks. So this first example I'm going to show you is from a numerical simulation of a thunderstorm that occurred quite a few years ago over in North Dakota and was associated with quite a few significant injuries, 22 injuries. The blue in this animation is the developing thunderstorm impinging on the tropopause, which is located right where the troposphere transitions to the stratosphere. That's right where the jet stream level is. And you can see as this thunderstorm impinges on the tropopause, it generates these waves. And the contours here, the white contours, are contours of potential temperature, which to a first approximation are markers for the fluid, the material surfaces of the fluid. And you can see in this example that they amplify and overturn, and the red areas are the model turbulence kinetic energy, and that's where there's turbulence, where these waves are overturning. And you can see that they can extend up to 5,000 feet above the actual thunderstorm. So you can think you're in a safe situation flying outside of the cloud, but actually it can be very turbulent if you have a rapidly growing thunderstorm. And just how far away from the thunderstorm top that the turbulence can be an issue depends on a lot of environmental factors, such as the vertical wind shear and how quickly the density might increase with height, above this thunderstorm, which is quite variable from case to case. Now, waves associated with thunderstorms can also move laterally away from the thunderstorm, not just vertically above the thunderstorm. And whether they move laterally for large distances or vertically depends a lot on these environmental conditions, such as vertical wind shear. And it's a complicated relationship, which I'm not going to go into. But in this example, you can see a case where I've highlighted an overshooting thunderstorm top, which is growing outside of the troposphere and into the stratosphere. It's generating these waves. And over a period of 2 hours, these waves expand about 2 kilometers away, or 200 kilometers away, I should say, from this source region, which is this overshooting top of the thunderstorm. In this particular case, it didn't produce very severe turbulence, but there are a lot of reports of light turbulence, light to moderate turbulence, pretty far away from the source region, which was where the strong thunderstorm was, but it's in this outer region of the cloud of the anvil on visible satellite imagery from the thunderstorm. Now, another situation where you often see cloudiness, which is related to turbulence, this banded cloudiness in particular occurs up near the jet stream. And in some cases, like the case on the right, these bands, which I refer to as transverse bands because they're transverse to the jet stream winds or the orientation of the jet stream winds, or in this case, transverse to this thunderstorm cluster, which is depicted here. They're a very common source of turbulence. And what's nice about these bands is you can often identify them beforehand on visible satellite pictures. And they're often associated with large collections of thunderstorms, like in this example to the right, which are referred to as mesoscale convective systems. And to just give you, because since all of you might not know about mesoscale convective systems, just a few definitions here. They're a collection of thunderstorms having a much larger horizontal scale than individual thunderstorms. An individual thunderstorm might be at the largest about 10 or 20 kilometers across. The smallest mesoscale convective systems have a scale of 100 kilometers or more, and sometimes they can reach scales of 500 kilometers or even greater. The typical life cycle of a mesoscale convective system is a late afternoon initiation, maximum intensity during the evening, and maximum size overnight. And they're very common over the central plains of the United States, where most of the warm season precipitation is associated with these mesoscale convective systems that happen overnight. States like Kansas, Nebraska, Missouri. They're well-organized internal circulations which can persist beyond the decay of individual thunderstorms. The most important one for this topic of turbulence near the jet stream level are the upper level outflows that occur near the jet stream level. And they can persist for a while, even past the decay of the thunderstorm and at quite a distance from the thunderstorm, and they can be responsible for widespread outbreaks of turbulence. Now, here's an example of a mesoscale convective system. This is a 10-hour loop of water vapor imagery from a case of about 10 years ago over the Central Plains. And you can see this very thin banded structure developing on the northern side of the mesoscale convective system. The active thunderstorms in this case are with the reddish and orangish colors down in southeastern Kansas and Missouri, but these bands are located way up in Nebraska and into northern Missouri. And if we stop this movie and just show a snapshot at one particular time, I've highlighted with the red ellipse these bands, and that's where all the turbulence reports to the right are in this right panel, which are light to moderate turbulence at the jet stream level. And there have been studies of these transverse bands associated with MCSs. There was one from about 14 years ago, and it found that about half of the large, long-lived MCSs over the continental United States had these transverse-oriented cirrus bands, and there was at least one observation of light turbulence in 93% of the cases, of moderate cases in 44% of the cases. So turbulence is very often associated with these bands, and they're at large distances from the thunderstorms. Now here is a case of transverse bands and associated turbulence that we studied quite a few years ago. It's a 2-day event which occurred over many states in the central US. And you can see the bands up on the northern portion of the mesoscale convective system. Active thunderstorms are about 400 to 500 kilometers away, which is about 250 to 300 miles away. So very far away from where the thunderstorms are occurring. And on the right, I have a fairly complicated diagram here, so I'm going to take a little bit to explain it. This is what is referred to as a Hofmüller diagram. The vertical axis is time. In this case, time is increasing downward. This is the vertical axis. The horizontal axis is latitude, and the latitude increases to the right, and higher latitudes are more northward locations. The colors are the rainfall average over a 10-degree longitude band, which is a distance in the central United States of about 750, 800 miles. And so it's the average rain over that distance, which is about the width of this mesoscale convective system. And one thing to notice here, and these contours are the strength of the vertical wind shear near the jet stream level. And with these red arrows, I have indexed the location of the bands on this Hofmüller plot for both nights in this event. And you'll see that these bands occur in the region where the wind shear is the strongest, where you have the most contours together. And this unit is meters per second over a depth of about 100 millibars. One thing to notice is that, and I'll illustrate it with this second night, the strongest wind shears in the bands are occurring about 5 degrees of latitude to the north of where the heaviest rain is, and about 2 or 3 hours after the timing of the heaviest rain. So they're associated with the heavy rain, but they don't exactly coincide both in time and space with where the heaviest rain is. And it turns out that the jet stream winds, which contribute to the strong vertical shear, are associated with outflow coming from these areas of heavy rain associated with the thunderstorms. And I have a schematic diagram in this next plot that can kind of show you how that happens. This is in a typical mesoscale convective system. Not all mesoscale convective systems look structurally just like this. But you can see oftentimes the heaviest thunderstorms in their mature stages are on the south end of the mesoscale convective system, closest to the strong moisture associated with a low-level jet of moist air that occurs over the Great Plains of the US overnight. But they produce these outflows near the jet stream level, which I've indicated with these purple arrows. And the outflows last a long time and travel a long distance. And because they last a long time, they can have some curvature due to the Coriolis force. And by the time they get toward the northeast end of the cloud shield of the MCS, they are in the same direction as the background jet stream winds. So they add to and enhance these background jet stream winds. So underneath the region where the winds are the strongest, you tend to get the strongest vertical wind shear, which I've indicated in this shaded region. And that's where you often see this banding in a climatological sense associated with MCSs. It's a little bit different in every case, and it depends on the orientation of the mesoscale convective system. Now, on the opposite side of the MCS, on the south side, you can see this outflow, and the outflow at the top of these mesoscale convective systems is anticyclonic. It's in a clockwise direction. Here, the direction interferes with the direction of the environmental upper jet, so the actual winds aren't as strong as they are on the northern side of the system. So it's a little bit complicated, but in a nutshell, this is why you often have preferential, you'll see in a satellite picture, preferential banding on one side of these mesoscale convective systems. Now, there are other types of weather systems that are associated with thunderstorms that also have this banding. On the left, I have an example of a hurricane, and you can see the banding, and there's often turbulence near these bandings, which you might experience on a hurricane flight, although the hurricane header flights tend to fly at lower levels where the hurricane winds or the hurricanes are the strongest. To the right is a case of a big wintertime low pressure system over the North Atlantic, and you can see a lot of banding. The banding in this case is occurring with some convection ahead of or thunderstorms ahead of a cold front that's associated with the jet stream. So in the final part of the talk, I want to talk about some fundamentals of turbulence forecasting. And I haven't mentioned yet exactly what you're feeling on an aircraft when you experience the turbulence, and what the actual aircraft response is due to variations in the motions over relatively small areas, like about 10 meters to maybe a few kilometers. That's what's affecting the shaking in the plane when you have these turbulence events. But it turns out that the numerical weather prediction models, which we base our forecasts on, our 1 to 2 day weather forecasts, or even longer now, they're not able to simulate these scales that are this small. They have much larger horizontal grid spacing, so they're not able to detect these scales of a few meters to several kilometers, maybe up to 5 to 10 kilometers. Now, it turns out that these research numerical weather prediction models, which I've been talking about, since you're able to run them in hindsight and not over as large an area, you can have smaller horizontal grid spacings up to about a factor of 10. The smallest horizontal grid spacing in these research NWP models might be, instead of 3 kilometers, which you would see in our highest resolution operational models. An example of that is the HER model, which some of you may have heard of, which we often use in forecasting thunderstorm systems. In the research NWP models, we can go down to maybe about 10 times as fine a resolution. That would be 300 meters or a third of a kilometer. And when you get down to those horizontal grid spacings, the scales that you can actually resolve is about 8 times the smallest scales you can resolve is about 8 times the smallest grid spacing. So 8 times 0.3, that would be about 2.4 kilometers. So you're just starting to get into some of the scales where you can actually have a response in the aircraft. So what this tells us is the onset mechanisms for the turbulence you can start to detect with these research NWP models, but you can't detect you can't simulate the fully developed turbulence. So this is a fundamental problem, is being able to link the outputs from these models to where you're going to have turbulence or strong turbulence. And this is an example of a turbulence mechanism. This is called Kelvin-Helmholtz instability, which I'm showing here. It's often responsible for a lot of the clear turbulence or turbulence outside of clouds. But when there's enough water vapor, sometimes you can see signatures of it in these billow clouds. In this case, this was associated with enhanced wind shear near a mountain region. You're not able to, with a operational numerical weather prediction model, simulate this. You can simulate the strong vertical shear, which I've indicated. And strong vertical shear, what I mean by that is just the large changes in wind speed with height or in wind direction with height. In this example, I've illustrated large changes in wind speed in one direction with height. In a research numerical weather prediction model, you're actually able to simulate down to the scales of these first overturning of these Kelvin-Helmholtz waves, the billows, but you don't see the fully developed turbulence. Operational models really can't even get that far. So we need different approaches in order to be able to forecast the turbulence. Now, this, what I'm illustrating in this plot is a strategy for a research model to be able to simulate the onset mechanisms for turbulence. It turns out that both the large scales and the small scales of motion are very important. So you need to be able to resolve simulate the large scale environment over a large region, such as the continental United States. So that is done in this outer domain where we have grid spacings of about 10 kilometers. And what we do is we have what are called domain nests, which communicate with each other. Each one of these domains, D2, for instance, communicates with D1. D1 provides the forcing for D2. D2, though, has a higher resolution, a smaller horizontal grid spacing, all the way down, in this case, to where we're trying to simulate the onset of the turbulence in D5, which has a grid spacing of, in this example, of 370 meters. And so in the next plot, I'm going to show an example of a simulation from this model set up for a research numerical weather prediction model. This was a case of an early spring case of lots of severe turbulence associated with a big low pressure system in the lee of the Rocky Mountains in western Kansas. And the black dots here in this plot indicate where there were in situ, the solid dots, EDR observations from these onboard aircraft flights of commercial aviation airliners. The open dots were where there were pilot reports of severe turbulence. And there are two main regions in which you have the reports of turbulence. One of them is in a region of very, very low satellite infrared brightness temperature. This is where a very strong organized area of thunderstorms are developing. A few of these flights got a little bit too close to the thunderstorms and experienced severe turbulence. But there's also in this comma head region in the northwest side of the cyclone, of the low pressure system, there's also a lot of severe turbulence, some of it above the cloud, some of it actually outside of the cloud. And on the right, I have an animation that lasts 30 minutes from the highest resolution domain, this domain 5 that had horizontal grid spacing of only 370 kilometers. And it shows the onset of Kelvin-Helmholtz billows overturning. So this tells us that in this particular case, a lot of the observed turbulence up in here may have been forced by Kelvin-Helmholtz instability or initiated by that in a region of strong vertical wind shear. And the vertical wind shear in this case was associated with very, very strong outflow from a large area, anticyclonic outflow emanating from this area of deep convection. And the reason why we could tell this is it's possible to go back and rerun these simulations without the effects of clouds. And we weren't able to produce this Kelvin-Helmholtz instability because the vertical shear was a lot weaker, because we didn't have the outflow from the thunderstorm region to enhance the shear near the jet stream. So it turns out that even though it's very far away from this area of strong thunderstorms, it does influence this turbulence that occurs in this region. Now, there's even a class of research models that has higher resolution than these research numerical weather prediction models, and these are called large eddy simulation models, and these are designed more directly for the simulation of turbulence itself. In this example here, I'm showing a large eddy simulation of a squall line, a large area of thunderstorms, and the squall line is outlined by this single black contour, and the color shading is EDR that is simulated in this model, and that's you might recall from earlier in the talk, our metric that we had for determining the strength of the turbulence. And you can see right near the leading edge where the deep thunderstorms are occurring, that's where the turbulence is the strongest. But there are also a lot of other areas in and around the turbulence, around the thunderstorm, where there's significant turbulence, light and moderate turbulence occurring for quite some distance above the thunderstorm, also extending outward in the thunderstorm anvil and beyond the region of cloudiness. Even there's an area of widespread light turbulence and even some moderate turbulence just above the thunderstorm. So the large eddy simulation models, they have horizontal grid spacings that are finer than the research NWP models. Typical spacings might be 10 to 100 meters, so they're better at examining the details of the turbulence, but they have to be run because they have such fine grid spacing. They have to be run over much smaller areas, so they lack the potentially important details on the large scale environment. So they're less suitable for the examination of specific cases, but they're suitable for looking at the fundamental reasons, why you're going to get the turbulence and where in the thunderstorm complex the turbulence might be most likely to occur. But for operational forecasting models, we don't first off, we have to run them in real time before the event actually occurs. So they don't have the benefit of hindsight that allows us to put the domains in the place where we want to simulate turbulence. They're run over a much larger area. They have time constraints, and therefore must use much larger minimum horizontal grid spacings, which are not able to predict the turbulence onset. So therefore, this real-time operational forecasting of turbulence requires more of a statistical approach. And typically what we do is we take output from one of these lower resolution operational numerical weather prediction models and use it to derive a statistical model that predicts where the turbulence is most likely. So we take large scale parameters that are well simulated by this operational numerical weather prediction model, including the wind shear and temperature, which are predictable. And then we weight these different parameters based on how well they're correlated with turbulence in past historical situations in order to estimate the likelihood of turbulence in this forecast. And it turns out that this can work very well for thunderstorm generated turbulence if the operational model, such as the HER model, for an example, which we use in the United States, is able to reliably forecast the timing, intensity, and location of the thunderstorms, which it actually does with pretty good consistency. So this is how we forecast the turbulence operationally. And one example of one of these statistical models, which we use the operational NWP model, such as the HER to drive, is called the Graphical Turbulence Guidance System. It's used at the Air Weather Service in Kansas City. The airline forecasting departments use it. It predicts EDR, which I talked about quite a bit in this talk, as a measure of turbulence. And we have EDR forecasts from GTGs, and we break them down into different categories. We can break down EDR due directly to, say, for instance, mountain wave turbulence, due directly to clear air turbulence or low-level turbulence, or to thunderstorm generated turbulence, which we term as CIT, and that's is an acronym standing for convectively induced turbulence. And on the right, this is an example of output from a GTG forecast driven by input from output from the HER, and it shows in the area where the yellow colors, likelihood of moderate turbulence, lighter turbulence in the blue colors. So this just shows the likelihood of turbulence associated with different turbulence types. And now, the final thing I want to show in the talk is an example of different types of turbulence cases where we've made forecasts with GTG. And this first case occurred several years ago over the Midwest in a upper level trough. Upper level troughs are typically responsible for bad weather near the surface, both within the trough and slightly to the east of the trough. And this showed a lot of reports of moderate and severe turbulence extending from Kansas City to near the Chicago area. And on the right, I'm showing the number of turbulence reports over a 6-hour period and the different altitudes at which this turbulence was reported in this case. Now, here's a very different meteorological situation. This was a case of a synoptic upper level ridge with very strong flow over the mountains, which produced a lot of turbulence near Denver and Salt Lake City. But in this case, there was a different vertical distribution of the turbulence. It had maximum and turbulence reports both below the typical cruising altitude and above the typical cruising altitude. And it turned out that there was a lot of wind shear above and below the jet stream in this particular case. And you can see that in both of these cases, the reports are tend to be located pretty close to the jet stream. So that's where a lot of the reports of turbulence at cruising altitudes are most common. Now, this is just showing a little bit of verification of how good our forecasts with GTG were of these two different turbulence events. On the left, I'm showing the first case with the trough, and the gray shading shows where there were thunderstorms. This is the reflectivity plot. This is like a radar plot of where the gray shading is. The color shading is where the EDR is predicted by the GTG system, and the colored dots is where there were actual turbulence reports of moderate and severe turbulence. So you can see they match up pretty well in this case, and they also match up quite well in the next case, which I showed associated with the ridge over the western United States. Lots of anticipated moderate turbulence where the reports actually were. So, what you can conclude from this example and examples of a lot of other cases is expert forecasting systems such as GTG, which are driven by operational NWP models, show some promise in anticipating these widespread thunderstorm influenced turbulence events when the upper level outflows from the thunderstorms, and they're coming from, you get outflow coming from these areas, the gray area where we have the thunderstorms, enhancing the jet stream up here, creating stronger vertical shear and inducing turbulence. So just to summarize, thunderstorm-generated turbulence presents a major hazard to commercial aviation, both inside the storms, which can usually be avoided by radar systems that they have on board the aircraft and from air traffic control centers where they have terminal radars, but also for significant distances above and up, and up to hundreds of kilometers away from the storms. So this is something that turbulence forecasting needs to be aware of. There are multiple different linkages between thunderstorms and related distant turbulence, including waves and enhancements of jet stream winds due to storm outflows. The thunderstorm-related turbulence is more favored under certain large-scale conditions, including enhanced wind shear. We have, to help us forecast turbulence and in hindsight to better understand it, we have high-resolution numerical weather prediction models and large eddy simulation models, and they can predict mechanisms for turbulence and where it's most likely to occur. Operational numerical weather prediction models, such as the high-resolution rapid refresh called the HRR, they cannot directly simulate turbulence. However, when combined with these statistically based forecast systems such as GTG, can be used very successfully to forecast thunderstorm-related turbulence, provided, and this is a big if, that the model accurately forecasts where the thunderstorms occurs. And we're still working on improvements to that, but that has become better in recent years. So that's the conclusion of my talk, and I thank you all for attending. And any questions, I can take them as from Henry, or my email address is listed down here. Thank you very much.
Stan, thank you so much for that. That was a very, very illuminating talk on turbulence, and we really appreciate you taking the time today. We've got a couple of questions already coming in. And so if anybody has a question, go ahead and type it in at this time. We'll try to see within the next 15 minutes how many we can answer. If not, Stan will try to follow up with you again via email. So Jackie wanted to know, is it likely that EDR reporting equipment may be required on all passenger aircraft in the future? And then should it be?
I don't really have a direct pipeline to regulatory, industries. It's expensive to develop and manufacture and install. And I think there have been increases. I'm not sure. It's not something that's regulated. I think my understanding, the FAA interacts with the airline and interacts with research institutions such as NCAR, and we highly encourage the airlines to use these systems, but there are logistics involved, and like anything, it takes a long time. But I think we're moving in the direction of having more of these systems on the commercial airliners. But I'm not the best person to ask for this, to be honest.
Okay, that's fine. And Lori was wondering, so when you were talking about the graphical turbulence guidance, and we're going to put a link to that when we can get one on our webpage, so you guys can look at that. But Lori was wondering, does the military use that also for their planes? Do they look at, or are they not really worried about turbulence?
I'm sure they're worried about turbulence, and they may do that. I should mention that GTG is just one forecasting system. It happens to be strongly supported by the Federal Aviation Administration, and that's where a lot of the funding for the R&D of GTG has come from at NCAR.
Okay, we have somebody want to know what the HRRR means. Can you explain what that stands for on the model?
Yeah, it is an acronym. It stands for the High Resolution Rapid Refresh Model, and that's just one of several models that is run at the National Centers for Environmental Prediction. These are the folks that produce the numerical model forecast guidance for forecasting of the weather in the United States. And the HRR, the HRR, was developed at NOAA, and it is a short-term forecast. It's a model that's used to forecast, weather events, including thunderstorms, over a time scale of about 24 to 36 hours. We have other models that forecast the weather for longer. The NAM model, North American model, which is a lower resolution model, but run over a larger area, forecasts for up to 84 hours. And the GFS, Global Forecast System, is our global model, which provides forecasts up to, I believe it's 384 hours now. And we have models that go even longer than that.
Okay, thanks on that one. Here's one from Michael, wants to know, are there any special challenges in modeling turbulence resulting from back building thunderstorms?
Yeah.
And we see a lot of those here on the Front Range. I know, I've watched them.
Yeah. Well, there's a lot of ways in that you can get turbulence from back building thunderstorms. They produce a lot of outflow that extends for long distances from the thunderstorms, and the back building thunderstorms, where they're back building, they're very often violent bursts of convection, which produce overshooting tops, which can trigger these gravity waves, which under certain conditions can break. It is very challenging, and it's a common source of turbulence. And in situations where you have back building thunderstorms, if you can identify them, you want to divert aviation operations as far away from them as is logistically possible. Sometimes it's not completely possible if an airliner is on approach, say, to an airport, but generally they're avoided.
Thanks. Here's one from Sean, and he flies. He's a private pilot. He flies below 12,500 feet usually. He mentioned that you talked heavily about impacts of turbulence to jetliners at high flight levels, but what kind of research has happened on the effects of turbulence, especially low-level turbulence, on light aircraft? Is there any thing going on with that?
There is a lot of research with that. And one thing I didn't mention about GTG is it forecasts turbulence at all different altitudes, from the surface or just above, up and well into the stratosphere, above typical commercial aviation altitudes and also below. One thing that these smaller aircraft typically don't have, although a few of them might, and I'm not positive about this, have these onboard EDR systems, but those are mostly confined to the larger commercial aviation airliners. But there is a lot of research going on for general purpose aviation.
Thanks.
As
Sean
well.
from Arizona. Yeah, Sean from Arizona has a question, and he wants to know, is clear air turbulence more prevalent in and around particular geographies or seasons? So do you find it that not the thunderstorm bug, but the clear air stuff?
Yeah, I think there's some evidence that it both occurs most often near jets, near the jet stream. But the jet stream, of course, varies in geographic location, but the mean position of the jet stream experiences a lot of that. Mountain wave turbulence often occurs in the clear air, and that's most frequent in the above and in the immediate lee of large mountain ranges such as the Rockies that can often have a maximum of turbulence. And turbulence associated with convection or thunderstorms might be slightly more common in the warm season just because there are more thunderstorms, but it can also occur in the winter when you have these large low pressure systems that have warm air on their east side, warm moist air on their east side. So it's sort of an annual problem, and it spans a wide range of areas, so it can happen just about anywhere.
Okay, thank you for that one. Curtis was wondering, is there a fertile area for AI to assist with model development in this?
Very, very good question. And there's a lot of research just throughout meteorology for that, but also in studying aviation turbulence. And one thing that I didn't mention about GTG is it produces both a deterministic forecast and an ensemble forecast. And AI methods are often employed to determine how to produce ensembles of forecasts. And by ensembles, I mean multiple different forecasts for the same time that are based on slightly different parameters that are analyzed or different initial conditions. So AI is becoming an increasingly more important part of this.
And another question, a different one from the same person, though, that we're wondering about turbulence. How will turbulence from thunderstorms change as climate change progresses? Is there any thought about that as we get into climate change, will it be worse? Any thoughts on it?
Yeah, there is some research in this area. This is just one example that I would give, but there are a lot of different examples. Is climate change. It's very possible that in climate change, the mean position of the jet stream may migrate northward, for instance, if there's more warming at the poles and than there is at the equators. That can influence both the strength of the jet stream and where it's maximized. So this is another active area of research. I personally have not been involved in it, so I'm not the best person to comment on it, but I do know enough to know that it's definitely going on.
Great. Well, we're going to take one more question here, and then the ones we haven't had a chance to answer, Stan will get back to you via email here in the next couple of weeks. But yeah, this is kind of a a personal one, and they were wondering, have you ever experienced turbulence? How bad was it? And tell people what it feels like. What does it feel like to I remember when I feel turbulence a lot of times, I try to close my eyes and say, okay, I'm riding in a car, we're going over railroad tracks. It won't last that long. So it may not be that bad. But personally, Stan, how about you?
Well, that's an interesting question, Henry, because I am very interested scientifically in turbulence, but I am not a particularly good flyer, I have to confess. I have mild claustrophobia, and intellectually, I know when the turbulence starts that I'm safe, but I don't like the sensation. I think that's probably a lot of people share my opinion. Some people like roller coasters and love it. The most severe turbulence I ever experienced was about 25 years ago in the winter on a flight from the old, actually it might have been even longer because it was from the old Stapleton Airport just before DIA. I think DIA opened in 1995. So this was just before that. And I was flying from Denver to Los Angeles in a mountain wave situation. And the pilot, when we were taxiing about to take off, warned us to get set to rock and roll because there had been reports of severe turbulence. We took off. It was smooth as glass until we got just over the mountains. And then it just became severely turbulent. The plane bounced up and down, lurched from side to side. And the overhead bins even came open. People were screaming. I was terrified, but fortunately it only lasted a minute. Nobody was hurt. And everybody was seat belted in because there was good preparation for it. And the flight the rest of the way to Los Angeles was completely smooth. So that's my turbulence story.
Those short turbulences, I think we can all say, okay, we can get through it. But when it goes on for 10, 15, 20 minutes, I think that really kind of wears on you. And, did the planes drop a significant amount in the turbulence, or is it just they stay within the parameter of, maybe 100, 200 feet, or can they drop a couple thousand feet in turbulence?
I am not really certain about what. I think some of the extreme drops can be as much as 1,000 feet, and those are the ones where there may actually even be some damage to the aircraft sometimes. But those are the ones that you might hear about on the news. That's pretty uncommon.
Okay. Well, Stan, it has been a pleasure to have you with us here for the last hour or so, and we really appreciate your talk here. We'll have this archived on our website for folks to listen to, and so we just want to say thank you. And we will have stuff posted on our website as well. This recording will probably be up early next week sometime. So thank you very much. Well, folks, as we close out today's program, we wanted you to know that our next WxTalk webinar is taking place on Thursday, June 29th. So go ahead and mark your calendars for that one. And it should be pretty exciting. It's all about wildfire, and presented by Tim Brown of the Desert Research Institute, that he's located in Reno, Nevada. And I've seen Tim's talks before, and they're always stimulating. So I think you really will enjoy this one. We currently have the registration information up on our website. And so if you go to our webpage and you click on WxTalk webinars, you'll see it right there. And then, folks, before I forget, before signing off today, please take the short survey that's going to pop up on your screen. So until we meet again, this is Henry Regis for the rest of the CoCoRaHS team saying goodbye for now, and wishing each of you a wonderful springtime week ahead.